Hello, everybody. So here we are with a circuit. Well, it's actually technically not a circuit. It's more like a resistive array because the circuit has to start and end. It actually has to connect the beginning and end points. So I'd have to have a source here between A and B. But that's neither here nor there. We're dealing with the circuits problem. All right, we're in the domain of circuit theory. A lot of people are looking at this and going, "This is what you introduce us to equivalent resistance with." Jesus, why? Because this has every type of connection that you can ask for, which is really just two, well, three. It has all the connections that you can ask for, and it's good practice in one shot. After you've done this, you should be pretty much okay with it, all right, after this one. So we have this huge thing, and then they say very specifically, find the equivalent resistance of this mess, all right, between A and B. Now, mind you, remember, whenever you are looking for whenever you're shrinking your circuits, whenever you're trying to find some equivalence, or whenever you're trying to reduce a circuit between something, they always have to tell you where you're reducing between. In this case, they say find it between A and B. Remember, A and B are your nodes of interest. They're basically functioning like the addresses of what you're looking for. It's like saying, oh, come to my house, and then I never tell you the address to my house. You don't know where to go. If they don't tell you how to reduce, if they don't tell you the direction to reduce toward, then you get stuck, because most certainly the reduction of this circuit between A and B is not the same as the reduction of this circuit between D and F. I assure you. Okay, if you want to challenge yourself, go and try to do the reduction of this circuit between D and F. You're not going to get the same thing. All right. So I don't even know if you actually be able to get that, but that's neither here nor there. So let's work it. All right. Basically, all I have to do is just shrink resistors in series, shrink resistors in parallel, and do that over and over and over. And it looks like we're going to go this direction toward A to B until we have one resistor between the nodes A and B. All right. So let's get to it. First thing you do is look for any situations where you see series connections. All right. If I'm going this direction, I probably want to start at the other end. So you have D connected to E connected to F. All right. 12 and 8 are actually in series. How do you know that? If you just start a current on D, spontaneous, and you make it and you draw it, it's going to pass from D to F without ever breaking off. At point E, it's just like a turn in the road. All right. It never actually breaks into two currents. And because of that, we just have the idea that these two are in series. All right. So these two right here, we're going to combine in series. So this one's going to be a long-winded problem. And I only have to make it long-winded in the beginning because you want to show every little step. But in the end, maybe after the next two examples, I'll actually be able to do these a lot faster. Oftentimes, when you've had the proper amount of practice, you can burn through these like in your head 2 steps at a time sometimes. All right. You don't ever want to do more than you're comfortable doing. So be wary. I'm going to put this resistor right here. You could put it at the top or bottom branch, the top or the right branch. A lot of people say, which one do I pick? It doesn't matter. If it's in series, you could put it here at the top or here at the right. It will not matter. This is 1.5. This is 2.5. This is A and B. This is 20. 1.8. This is 10. This was 20. This is 16. This is 20. And these 12 and 8 together, you add them, all right? So this right here is going to be series. I'll actually just make the note. That's 12 plus 8, all right? That's equal to 20. So this resistor right here is going to be 20, okay? Based on how this is written, this is going to be C, D, D. E dies away when you combine the 12 and 8, all right? The resistor between the two dies. That's just how it works. So this is what we have. Now from here, I'm going to do a big jump, and I want everybody to follow me, all right? I'm going to explain every last bit of it. Take a look. A lot of students will look at this and go, well, they have these diagonal sections. What do I do with that? Forget what it looks like. Pay more attention to what it's between, all right? Nodes are addresses. They're important. Do not look at the way a city is, I guess if you look at a bird's eye view, don't look at the bird's eye view. Don't pay attention to that. Pay attention to what's sitting between what. All I see is a bunch of streets and avenues just stuck between each other. So what I'm going to do is I'm going to redraw this in a way that looks a little bit more convenient after I make this first statement. If you look at this resistor 20 is sitting between D and F. Okay, good. This resistor 20 is sitting between D and F. Okay, well, if this is between D and F and this is between D and F, remember the definition of series is they both have to be between the same two nodes. So these two right here are in parallel. But we're actually not done. You could combine these two in parallel, but then you'd realize this 16 is between D and F. All right, so this 16 is in parallel with 20, and it's also in parallel with 20. So all three of these are in parallel, and I could combine them. But then if you keep going, you realize you still have more parallel. This 20 is also between D and F, and this 10 is also between D and F. So I have 1, 2, 3, 4, 5 resistors all between D and F, which means all of them can be combined in one giant parallel equation. I'm not going to do that. I actually don't like using the 1 over R equivalent equals 1 over plus 1 over plus it. So I just end up messing the math up. I'm not really that great at arithmetic. But what I am going to do is redraw what this will look like for those of you who are not seeing it. All right. And just kind of put them together 2 by 2. All right. So I'm going to say it right now, and I guess I'll do it in green. There we go. All of these right here are actually in parallel. And then for those of you who are good with it, you could just say 1 over the equivalent resistance in parallel equals 1 over 10 plus 1 over 20 plus 1 over 16, oh Jesus, plus 1 over 20 plus 1 over 20, and then solve that for REQ, the parallel block, all right? Before I do that, I'm actually not going to do that. I'm actually going to redraw this in a way that looks a bit more familiar to the students. And I'm also going to make it a little bit bigger. So this is 1.5. This is my A here. This is my B. This is my 2.5. This is my 20. Then I have my 1.8 right here. Now, if everything is between D and F, and this is D, this is C, just draw a long line on D. I have 5 pieces. As long as it's between D and F, it does not matter how you draw it. So if I go 1 between D and F, 2 between D and F, 3 between D and F, 4 between D and F, 5 between D and F, this configuration is the exact same as the one that I just came from. So this is 20, this is 20, this is 16, this is 20, and this is 10, okay? And all of that is between D and F, all right? So for those of you who don't like the way this looks right here at the top, this top right piece, you can just redraw it like this at the bottom left, and if it's more convenient for you, then great. But I have the same exact statement. This is parallel, so this idea is still happening, okay? Still happening right there. What I'm going to do is I'm just going to kind of jump through some of these in my head really quickly, and I'll just kind of give my notes on what I'm doing. So I'm going to take this 20 and this 20. They're in parallel, all right? So remember, here's a little trick that I like to remember. When you have 2 resistors in parallel and they're the exact same value, you can do 20 times 20 over 20 plus 20. But what happens is if they're the same, they always give you half of what they are. So 20 in parallel with 20 is always going to give you 10. Okay? So here's what I'll do. I'll have a line like this. I'll say 20 and 20 is going to give me a 10. All right? And then what I'm going to say is this is a 10, and I'm going to combine this 10, because remember, these two are now together as 1 10, and I have a 10 over here. So 10 and 10, all right, I can actually do that. I don't have to go all the way, left or left or lower. I'm going to go 10, and I'm going to combine with this 10, all right, and as long as I have my arrows drawn properly, you should be able to see what's happening. So this 10, so I'll say a 10 right here, and this 10 together are going to give me 5. Okay, so now I had 3 resistors. 3 resistors is broken down into 1 resistor. So I have 1 that is 5, the 20, and the 16. So I have 3 resistors left. All right. Now from here, and this is just because there are little things that I remember, little combinations that I remember. Anything in parallel with itself, it gives you half. 6 in parallel with 3 gives you 2. All right. 20 in parallel with 5 gives you 4. Okay. Let me put it in green. The 20. Oh, this is going to be, that's in green, so it won't matter. The 20 in parallel with the 5, 20 times 5 is 100 over 20 plus 5, that's 25. 100 over 25 is 4. 20 in parallel with 5 is 4, and now I have the 4 in parallel with the 16, okay? So the last one I'll do in another red because I've gotten away from it all. And I know a lot of people are like, why is he doing this? Why doesn't he just put it in this equation? You can put it in this equation. You're going to get the same thing I'm about to get. I just prefer to do this. It's all a matter of preference, honestly. Once you've learned rules, everything is a matter of preference. Finally, I'm taking my 16 in parallel with my 4. You get 16 times 4, which is 64, over 16 plus 4, which is 20. 64 over 20. Okay, and that's going to be 3.2. Okay, so I have a 3.2. All of this stuff together, the answer to this problem right here, remember you have to flip it, is actually going to equal 3.2. So I can redraw my statement now. So I have this right here, this right here, this right here. Okay, this 1.8, and then this was D. And now instead of the 5, I have one resistor that's there with a 3.2. This was 1.8, this was 20, this was 1.5, and this was 2.5. Okay, so you want to have a good conceptual understanding of what's happening. All right, if you don't see what's happening, if you can't like visualize and just start making sense of what's going on, then it's going to make life a lot harder for you, especially when you're doing circuits. These two together, if this 1.8 and 3.2, if you just draw spontaneous current, you see that the current never breaks. All right, because of that, they have to be in series. Okay, series. I'm going to have 1.8 plus 3.2. And that's going to equal 4 or 5. All right. So I'm going to have a resultant 5 sitting there in parallel. Well, I shouldn't say it yet with the 20. So here we go. This is my 20. Okay. This is my 2.5, my 1.5. This is my A and B still. And now what was now 1.5 and 1.8 and 3.2 is now reduced to one resistor of just 5. All right. Now the D got killed when I combined these two in series, excuse me. So what was left was C, and this at the bottom would have been F. If 5 is between C and F, 20 is between C and F. So these two together right here are parallel. Okay. So I get 20 times 5 over 20 plus 5. That equals 4. Okay. That's also something you want to just remember certain parallel combinations. 6 and 3 gives you 2. 20 and 5 gives you 4. I cannot remember right now which one gives you 3. I think it's 8 and 6, but I'm not sure. I have to see it. Okay, so finally I have my A, my B, my 1.5, my 2.5, and these two together gave me a 4. All right. So this is C, this is F, but honestly at this point they don't matter. Why? If I draw a spontaneous current and I just have it pass, it's going to pass through all of these without ever breaking away and creating other currents. These are all in series between A and B. Okay, so I'm going to have 1.5 plus 4 plus 2.5, and that's going to be the 2 and the 1 give me a 3, and the 4 gives me a 7, the 0.5 gives me an 8. All right, 8 ohms is what's sitting between A and B. So the final picture is going to be A, one resistor between A and B, and that's going to be 8, the answer. Okay, so a little bit long-winded, but it's okay. This is just the first example of many of our resistor reduction problems. You're going to need to reduce stuff all throughout the course, all throughout any circuits class, all right, all the way up to like electronics. So you want to get good at this. You want to start seeing stuff from a fundamental point of view. Don't look with your eyes, all right? Pay more attention to what's sitting between what two nodes, all right? And if I were to generate a current, if the current were to ever break, use those ideas to identify series and parallel. Not, oh, those are right next to each other, so those are in series. No, that is not how it works, okay? Because of that idea, a lot of people would look at this set right here, and they would say, oh, the 1.5 and the 1.8, they're in series with each other because, they're next to each other. No, that's not true. If I were to draw a current, let me get rid of those two. If I were to draw a current passing from the 1.5, it would come and it would hit C. It would hit C, some of it would go that way and some of it would go down. Because of that, it has to be not in series. That doesn't mean it's in parallel. Remember, you have series, parallel, and neither. All right, but 1.5 and 1.8 are almost certainly not in series, and they're also not in parallel because they're not between the same two nodes. 1.5 and 1.8 are in the neither connection, and they stay in the neither connection until you reduce all the way from the right side to the left. All right, you got to practice this. The better you get at this, the faster you'll be at this, and the easier your circuits will be to solve. Okay, you want to develop what I call foresight, which is your ability to see the next circuit before you actually write it down. Okay, it's going to save you a lot of time in your circuit solving. All right, so I hope this helped.